Hello everyone, you're welcome to this channel once again. Today we shall be discussing on a particular question from mass dynamics once again. Now let's read to the question given to us today. A uniform massless rigid bar is pivoted at point A and is connected to 4 linear springs with stiffness K equals 300 Newton per meter and 1 rotational spring K theta of 3,000 Newton meter per radian as shown in the figure. If the mass of the body M is 10 kg and the length of the bar, that is the massless rigid bar, is 1 meter, calculate the natural frequency of the system, that is Wn, assuming the system is moving in a horizontal plane. Once again, a uniform massless rigid bar is pivoted at point A and is connected to 4 linear springs with stiffness K, which is 300 Newton per meter, and 1 rotational spring with stiffness K theta, which equals 3,000 Newton meter per radian, as shown in the figure below. If the mass of the body equals 10 kg and the length of the massless bar equals 1 meter, calculate the natural frequency of the whole system, making assumption that the system is moving or is in dynamics of horizontal plane. Now, first of all, by pulling out all our parameters given here for the whole system, should be the first instance. We have the case constant of the system, each one equals 300 Newton per meter. We have the K theta, that is the stiffness of the rotational spring, equals 3,000 given. We have the mass of the body, 10 kg. We have the length of the whole massless rigid system. Now looking at the 2 springs connected in parallel, the law assumes that whenever a spring is connected in parallel, just like we have here, they will be added to each other. So therefore, the summation of the spring connected in parallel here becomes K plus K, which equals 2K. Now we know that the length of the connection of the equivalent of the stiffness, which is 2K, is L over 4. So therefore it becomes 2K multiplied by L over 4 multiplied by the angle of rotation given. So therefore it becomes 2K L over 4 multiplied by theta. That's given. Now looking at the mass position 2, where the mass is situated, we have the 2 springs connected in parallel. So therefore it becomes 2K multiplied by the length of the rotation, which is 3 over 4L, multiplied by the angle, which is theta. So that gives us 2K 3 over 4L multiplied by theta. That's given. Now, don't let us forget that the rotational spring 2 has a rotation. So therefore, the K theta will be multiplied by the angle of rotation 2. So that becomes K theta times theta. That's given 2. So now that we have solved all the static equations for this particular system, now we can equate it to the dynamics of it. That is when the body is moving, knowing fully well that there will be a rotation at the midpoint, at the point of the pivot. That is the point of the pivot here. So from the dynamics point of view, we know that the rotation equation will be j theta dot dot, which equals ml square theta dot dot, which we are given. So j theta dot dot equals ml square theta dot dot. Now, by equating or linearizing the dynamics to the static equation, we have the equation of motion that say summation of all the moment about zero equals j theta dot equals ml square theta dot. That gives us m into bracket 3 over 4 L square into theta dot equals 9 over 16 ml square theta dot. So, and we know that by equating both equation here to here, that gives us this. So from there we can juxtapose our resolved equation here to standardize equation of body dynamics, which is m theta dot plus c theta dot plus k theta equals 0. So therefore we can deduce that our m equals 9 over 16 ml squared and our k equals 5 over 4 kl squared plus k theta. So therefore, by inputting these both values into equation of natural frequency formula, that is Wn equals k over m root, we have this particular equation slotted. So that gives us the root of k over m, which we have been given to be 24.50 radian per second. Once again, our calculated natural frequency for the whole natural system given here becomes 24.50 radian per second. Thank you very much.